Okay, hello, welcome back. Let me address. All right, so we have so far seen what the degrees of freedom are and what constraints do to the system and to the number of degrees of freedom of the system. The last thing we want to discuss is the idea of what is called generalized coordinate. And as the name suggests, it's a generalized version of coordinates. Let me show you what we mean by that. Let's pretend we have a 2D space for now, and I have 3 particles. So what I can do is get the coordinates of each of these particles, and I have 3 particles. Each of them has 2 degrees of freedom. I need 6 numbers. Six coordinates of these particles are enough to describe the system. Alternatively, what I can do is instead of working with the coordinates of the particles themselves, I can, for instance, look at a different version of coordinates. So the first one is probably the same coordinate as, you can call it a polar coordinate. But extending that idea, we can choose a different, or no, maybe let's do this. Choose, instead of x and y of the other coordinates, I can choose something maybe relative to the previous one. So these two are new, let's call them generalized coordinates that I can use to describe the object. Maybe this is the last one. So you can see, instead of working with the probably in the same axis and reference frame, working with the coordinates of your particles, you can work with a slightly different versions of those particles. They're called generalized coordinates. So in the previous lectures, we saw how we can find acceleration velocities and all of these concepts within a framework. Now, the goal from here on for most of the class is how we can extend these ideas, and instead of working with position velocities in a given reference frame, aka the actual coordinates and velocities in those frames, work with the generalized coordinates and velocities in those spaces. So that is the idea of generalized coordinates. It's nothing fancy. It's just an extended version of what we call coordinates. They can be arbitrary. And one thing important and useful, the units and dimensions, dimensions of generalized coordinates could be different. So in this case, could be different from one another. One another. So what I mean, let me go back to x and y. I can have, please, I can have x and y of the first particle with units of meters or whatever, and the next one could be some kind of angle, and so on. So it is possible to mix and match in different domains and different dimensions to build our generalized coordinate to describe a system. One other thing, let me use almost the same example, but instead of having individual particles, let me do this. So these are the same thing. The only thing I did, instead of having variable distance between them, now I'm working with a fixed distance between the particles, so essentially building a mechanism. So again, here I don't need to specify the distances r's because they are fixed. So the only generalized coordinates that I can have would be these three angles. And in this case, I need to specify these three, theta 1, theta 2, and theta 3 to fully describe the mechanism and its configuration. I can arbitrarily fix this part as well, build a 4-bar mechanism. I still have these three generalized coordinates to describe the system, but now I have added a constraint, or a couple of constraints possibly, in the x and y direction of the last point. So I still have three generalized coordinates, but my degrees of freedom, I only have one degree of freedom. So we saw before, for 1 degree of freedom system, we only need one variable to define this. So actually, among these three generalized coordinates of theta 1, theta 2, and theta 3, they are not independent. Actually, there are some phi 1 of theta 1, theta 2, theta 3 equals 0. That is constraint 1. It could be that this is x of this tip, end of the particle being equal to something, or not equal. And I can have a constraint for y of the tip and some phi 2, theta 1, theta 2, theta 3 equals 0. So I have three coordinates and they're all dependent. And I need only one variable, and that is called the minimal set of generalized coordinates. So I only need one, and possibly, I don't know, let's call it theta 2, because I don't want to use theta 1. That is the minimally set of generalized coordinates to describe a system fully. And what else did I want? And this has the same number of elements, or the sets, the lengths of the set. I'll put it here. Length of the set equals number, or degrees of freedom. Number of degrees of freedom. All right. So that is the idea of generalized coordinates. Nothing, there isn't really anything beyond that. And the last terminology or concept we want to talk about is configuration space. Configuration space. So we can have a system that is described by n generalized coordinates. So I have n generalized coordinates, and we usually describe them by letter Q. So they form I can write them in a vector, and they reside in an n-dimensional space. This space is what we call the configuration space. So essentially, the configuration of my system is a point, an n-dimensional point shown by this vector in that n-dimensional space. So maybe in the example of the 4-bar mechanism, I have the theta 1, theta 2, theta 3. This is my configuration space, config space. And any point, theta 1, theta 2, theta 3, is a point in that space. So a few maybe notes. Usually, number of generalized coordinates or these q's, let's put it, number of q's is smaller than number of actual how do I say, number of ungeneralized coordinates. I don't know how else to write it. Coordinates in a system. And we saw it in the example above here, that I needed, in this example, I had three particles, each of them needed 2. I had six coordinates in the XY reference frame, but only 3 generalized coordinates to describe the same system, basically, using the angles. Well, actually, no, that's not exactly the same match. Let's pretend these lengths are fixed, and I'm looking at the XY positions of the tips of each of these links. Still, I need 6 XY pairs, but by looking at the generalized coordinates, I only work with 3. And also we saw that the minimal set, we only need 1 generalized coordinate to fully describe a system given certain constraints that exist within the system. Let's see what else. Yeah, let me write this down too. If we have n q's and m constraint equations of phi j, or in this is the holonomic case, usually we write it as fj if it's non-holonomic. Holonomic and non-holonomic constraints. Then the degrees of freedom, DOF, is n minus m. Or if you have n generalized coordinates and your system is, I don't know, k degree of freedom, you have n minus k constraints. Okay, so there is one other thing that I can leave it for next video. So for now, that is all we have for this lecture. So we talked about the ideas of degrees of freedom, constraints, and generalized coordinates. That kind of combines the 2 ideas. All right, so that is all for now. And in the next lectures, we will start talking about work and momentum in these generalized coordinate space. All right, so until then, happy studying.